Okay, we're going to start recording now. Okay, guys, so welcome to the second part of linear transformations. Okay. So I remember last time we have talked about, if I remember correctly, about linear transformation, as you can see here in the in the notes, the last notes from last time. We talked about a linear transformation given by a matrix. Since before that we wanted to see if this map, right, if this transformation, which is given by the matrix, well, we said in general that this holds true for any matrix. I see some people. Yeah, I had an exception from. No, only very few people are allowed to be back on campus. Those who are teaching or those who have something to do, and I'm allowed to be on campus around only this time, between 2 and 4 p.m. on Tuesdays. That's it. Any other time I can be allowed on campus is when nobody else is on campus, something like, I don't know, 9 p.m., 10 p.m., midnight, when nobody's there. So the thing is that we have to interact with as few people as possible. So yeah, I got an exception since I have to teach, and my internet at home, it's a mess. All right, so this is what we did last time. So keep this in mind, because linear transformations can be given by a matrix, and this will always be a linear transformation. As you can see here, TV is AV. Okay. That's great. So today we're going to veer towards something else. We want to do more material. So we will talk about the kernel and the range, the kernel and range of a linear transformation. Okay. Let's start with the kernel of a linear transformation. And you will have, I want to tell you from the start, we will have problems like this on the final exam. I will guarantee it to you. But anyway, when we will have our review session, you will see more about what will happen at the exam. All right, and let's start with the definition. So we have the following definition. I'm going to consider a map from V, sorry, to W, from two vector spaces, V to W, be a linear transformation. Be a linear transformation. You know what that is at this point? Then the set, and I will consider this following set. In fact, let me say it in words. The set of all vectors, let's say V in V, so in my vector space V, that satisfy T of V equals 0, right? Is the kernel of T. So that's the kernel of a linear transformation. And it is denoted by, let me write it, by kernel of T, ker of T. This is how we're going to denote the kernel of a linear transformation, right? Okay. And now let's see some examples. I think you got used to my style by now. I always like to do examples once I have a definition theorem before I even tell you more about, I don't know, the proof or something like that. I always like to stick to examples so that you can grasp the notion better. So the example I have in mind is the following. Let me consider T from this time from M32 to M32. So M32 is the set of matrices with 3 rows and 2 columns, right? These are not square matrices. And T of A, so my linear transformation, and we have seen the sense all matrices A to A transpose. And we have seen the fact that this is a linear transformation. The question is to find the kernel of T. So how do we find the kernel? That is the question. So this is a very simple example, right? And well, let's see, what is the kernel? If we look at the definition, so if we look at the definition here, somebody has its mic on. Anyway, I would not mind any music, but some people might be disturbed here. So, okay, so we want to see the kernel. And if you look at the definition, the kernel is the set of all vectors V in my vector space V such that T of V is 0. Keep in mind, look at this guy here. T of V is 0. So in other words, in my case, my vector space V is the set of M matrices, 3 by 2 matrices, right? And my if I want to find the kernel, I have to look at this equation. So T of A equals O32, right? This will be equivalent with, let's see, who is T of A? T of A is A transpose is equal to O32. But if the transpose of a matrix is the null matrix, guess what will happen to the matrix? Then indeed, this will follow that A is indeed the null matrix. 032. So the kernel is what? So the kernel is the kernel of T is given by this matrix 032. That's it. Okay. Now this is example 1. It was very easy. Let's see example 2. So I'm going to start with some easy examples first, so that you can. Let's see. Let's see, the kernel of the 0 transformation let's say T from V to W, right, consists of all vectors, of all vectors V in V, because T of V is always 0, right? For all V in V. And that is the kernel of T will be the entire vector space because it's the 0 transformation. It already contains that. Okay. Another example. Now, if I look at the kernel of the 0 transformation, right? I want to look at the kernel of the identity. The kernel of the identity transformation let's say T from V to W. In fact, here in this case, is identity goes, okay, from V to V. Consists of the single element And that element, guess what? It's what? It's 0. That is kernel of T will be nothing else than just the 0 element, right? Because the identity, keep in mind that the identity is T of V equals V. And we say that kernel of T is nothing else than all vectors V, look at the definition above, for which T of V equals 0. So in my case, T of V equals 0, which is this, will imply that V equals 0. So it will consist only of a 0 vector. All right. I hope it makes sense. Okay. Now let's see some another application, which is a little bit more involved, but not as hard as the example 3. Let's see. Let's find the kernel. Find the kernel of the linear transformation T from R2 to R3, and this T of x1, x2. So this T is given by T of x1, x2. As you can see, the domain is in R2, so have T of x1 and x2. This is x1 minus 2x2, and I have to consider a vector in R3. So the one component will be x1 minus 2x2. The second one is 0, and the third one will be negative x1. Okay. So I have to find the kernel of this, right? So let's look at it. And keep in mind the definition. Let's go back to the definition, and so the definition says that if the kernel of the linear transformation of all from a vector space to another vector space will consist of those vectors for which T of V is 0 for any V in the first vector space. So in our case, we need to find all vectors in R2, which will look like this, x1 and x2, such that T of x1, x2, which is given by this guy, equals the 0 element in R3, which is 0, 0, 0. And you already know what it means by now. For two vectors to be equal, this will be equivalent with the following system. Again, we end up with a system of linear equations. Is x1 minus 2x2 is 0. 0 will be 0. Thank God, otherwise we would have had a problem. And negative x1 is 0. Well, it's quite easy when you solve this system, and I'll leave it to you as an exercise to figure it out, but I think it's evident by now. From the third equation, it follows that x1 is 0, then you can plug it into the first equation, and then you go. So you'll have a unique solution, and the second equation is redundant. So the unique solution is given by x1, x2 equals 0, 0. So the kernel of T.
What was the anime called?
So the kernel of T will consist of this vector, 0, 0. And that's it. Which, if you want, you can regard this as the 0 vector. This is the 0 vector in R2 if you want to look, if you want to write it like this, but anyway. But to spare people of confusion, just keep the first one, and I think that should be enough, right? Okay, is it clear, this one? Do you have any other questions? Okay. Now, let me give you another example. So I want to do as many examples as possible. This was example number 3. Example 4. And this example would be of the same type, but a little bit different now. We said last time that we can represent linear transformation in the matrix form. So we will want to see one such example to find the kernel of one such linear transformation. So find the kernel of the linear transformation I think, Brianna, you have your mic on. For the kernel of the linear transformation, let's say T from R2 to R, no, let's take from R3 to R2. Okay, and this will be given by the following. T of X is AX, and we have seen that this is a linear transformation when we apply the matrix to a vector where my matrix, where A, oh my, just give me 1 second to, so when my matrix A is given by the following, give just 1 second. All right, so okay, so my matrix A is given by the following: 1, -1, 2, -1, 2, and 3. Okay, I want you to look at this problem, think about it for a bit, and just think about it, and we'll see immediately. So how would you approach this problem? Well, let's go at the definition of the kernel, right? It says the kernel, keep in mind that the kernel of T is the set of all vectors, let's say x, x1, x2, x3 in R3 such that T of x1, x2, x3, let's keep in mind, let's not forget how my linear transformation is defined. It's defined from R3 to R2 equals 0, 0, right? So that's the definition. And now I have to look who is T of X, right? In my case, X is x1, x2, x3. So T of X is AX, which is this matrix here, 1, -1, 2, -1, 2, 3. And we apply this to this vector X, which in our case will be a column vector, will be x1, x2, x3. Or we can say that this is a matrix. Okay, I want to ask you, the first matrix will, what type of matrix is it? Of what order? Can you tell me? So it's a 2 by 3, right? Like Blake says, 2 by 3. And the second one will be, is what? 3 by 1, correct. And when you multiply this, you'll get a, so we, 2 by 1. So this is, all right. And now let's multiply this. And once we multiply everything together, this will be equivalent, right? Because I have, as you can see here, I have 0, 0. So this will translate into my, to this matrix, this 2 by 1 matrix 0, 0. So this will be equivalent with the following system of linear equations. Again, we have a system of linear equations. And this, after some computations, this will give us x1 minus x2 minus 2x3. I hope I'm not equals 0. And the second one is negative x1 plus 2x2 plus 3x3 equals 0. As you can see here, this is a system of 2 equations, 3 variables. And as you can see, the number of equations is not the same with the number of variables. So how many solutions do you think the system will have? Do you think it will have a unique solution, for example? Just by looking at it, what's your hunch? Do you think it will, what do you think? Solution will depend on x3. Okay, be more specific. So it will have infinitely many solutions, right? So by writing, so we'll be tempted to say that this will have infinitely many solutions. Okay, now we write the augmented matrix. So once we write the augmented matrix, so let's write it. This will be 1, negative 1, negative 2, 0. Right? Again, I'll have 0. This is negative 1, 2, 3, and 0, right? So this is the augmented matrix. And once you do elementary transformations to this matrix, in fact, you don't even need to go there. You can just solve the system directly by just, like Morgan says, you can parameterize x3, for example. But anyway, you can do it whatever you want. So once you do this row of elementary row operations, let me put it like this. You will get at the end that the solutions, and I'll leave it to you as an exercise to figure this one out. You'll get at the end that the solution will look like this. So we get that x1 equals x3 and x2 equals negative x3. Therefore, at this point, we can parameterize let's say x3 to be t, and this t is a real number. And we can write the others in terms of this. So in other words, we can write the family, and this will produce, this produces the following family of solutions. Family of solutions, which is given by, and I'm going to write it like this, x1, x2, x3. And this will be given by, let's say, t So we say x3 will be t, we parameterize it like this, then x2 will be negative t, and x1 will be t. Okay. Or if you want, you can factor a t here, and you can, this will be t times 1, negative 1, and 1. Therefore, the kernel of T is given by the following. Okay, and we can write it like this, or you can write it as a column. It doesn't really matter where T is a real number. That's the set. Or if you want, you can say that the kernel is nothing else than just the span of this vector, 1, negative 1, and 1. That's it. This is how you find the kernel of this linear transformation. All right, let's do another one of this type. And this next one will be a little bit more involved, but anyway, I want to do it. So example number 5, like I said, I want to do as many examples as possible. And again, I will define a linear transformation in terms of, which will be given by a matrix. So let's define the following. Define the linear transformation T from R5 to R4, oh my, which will be given by the following. T of x is AX, where x is a vector, is, let's say, is in R5, okay? And the matrix A is given by the following. Let me see if I have enough room here. Okay, probably I will. Okay, so my matrix is given by the following: 1, 2, 0, 1, negative 1. Then 2, 1, 3, 1, 0. Then negative 1, 0, negative 2, 0, 1. And the last one will be 0, 0, 0, 2, and 8. Oh my. So let's look at this matrix. It will have 4. So what kind of matrix is this? What is the dimension of this matrix, if you look at it? It's a 4 by 5, right? It has 4 rows, 5 columns. And what we're asked to do is the following: find a basis for the kernel of T, for Ker of T, as a subspace of R5. All right. So you see the task here is a little bit different. We need to find a basis for this kernel of T as a subspace. But before we do this, we need to find a kernel, right? So we will use the same procedure as in the previous example, and we will write the augmented matrix, as you can see here. So as in the preceding example, we had to write a, okay, so we will use the same procedure as in the previous example. Okay, and now we're going to write the following. we're going to write my matrix. Okay, let me write it again. So keep in mind that T of x is given by AX, which will be my matrix 1, 2, 0, 1, negative 1, then 2, 1, 3, 1, 0, then 1, 0, negative 2, 0, 1, and the last one will be 0, 0, 0, 2, and 8. Okay. Somebody has his mic on. Derek, I think that's you. Okay. And I have to multiply this by a vector in R5. Pay attention here, which will be x1, x2, x3, x4, x5. Oh my goodness. And this will be the vector 0, 0, 0 in R4. Okay, so that's what we have to do. And guess what? Once you multiply all this, so multiplying, doing all these operations, in fact, we will obtain a system, and the system obtained, which I'm lazy to write out, but I can, okay, the system obtained will have the following. Augmented matrix. And let's write it. Well, it's kind of easy to write. The augmented matrix, so it's A0, which will be given by the following. Let's write it here. So on the first, we'll have 1, 2, 0, 1, negative 1, 0, right? And that's going to be a big one. God knows. Anyway, the second one will be 2, 1, 3, 1, 0, 0, 1, 0, negative 2, 0, 1, 0. And the last one will be 0, 0, 0, 2, 8, 0. Oh my goodness. So this is the augmented matrix. Look at it. What a beauty. And once we perform elementary row, we will reduce this matrix to its row echelon, reduced row echelon form. I'll leave it to you as an exercise. I don't want to exercise to do row echelon form. Well, you want to reduce this matrix to row echelon form, and after you do this, you will get the following system. After that, we will obtain the system, the following system. Okay, let's write it here. S will be x1, let's see, x1, okay, minus 2x3 minus x5 will be 0. Okay, then the next one will be x2 minus x3 minus 2x5 will be 0. And then the last one will be x4. I have plenty of minus plus 4x5 will be 0. Okay. Guess what? When you have this kind of system, you can expect again to have infinitely many solutions. So S will have has infinitely many solutions. Well, let's see, you can solve this by hand. It's quite easy. We just, for example, you have that x4, yeah, you can easily do it, but you can parameterize, so we parameterize, let's say x3 to be s, we'll have two parameters here, and x5 to be t, with s and t real numbers, right? Okay, once we have this, then we can write the solutions will be something like this. So x, the solutions, okay, the solution of our system S is given by the following. X will be, let's write it in this way, x1, x2, x3, x4, oh my, x5, which will be given by, well, you'll figure out as an exercise, but I'll just tell you in advance, negative 2s plus t. So you can write all of them in terms of x3 and x5, basically in terms of s and t. Then the second one will be s plus 2t. Then the third one will be s, then negative 4t, I think. I hope I'm not doing any mistakes. And will be nt, right? Anyway, you can write this as a linear combination of this two vectors. So it's s times negative 2, 1, 1, 0, 0, plus t times this vector, which is 1, 2, 0, negative 4, and 1. Okay. In other words, the basis for the kernel, guess what? It will be given by these vectors. So that's the kernel, right? So a basis for the kernel is let's say B from basis, which will consist of these two vectors, and let's write them as row vectors. So it will be negative 2, 1, 1, 0, 0, and the second one will be 1, 2, 0, negative 4, and 1. Okay, that's it. It was a little bit computational, but you know, at the end of the day, it's the procedure is the same. It's not okay. Do you have any questions so far? Is it clear? Okay, so everything is clear. That's good. Oh my! I hope it's not COVID thing going on. Although I've been to some places where COVID, where everybody got COVID, but except me and my friends. I don't know how this happens. Anyway, so this is a basis for the kernel. And now I want to stress the following. I want to stress out the following fact, and which is given by the following theorem. Let T, and I'm going to consider this time a linear transformation transformation from Rn to Rm. So let T be from Rn to Rm. This is very important, not just for one vector space to another. So be a linear transformation. And this linear transformation is given by T of x is Ax, right? It can be represented by a matrix. Then I'm going to write in words, and then I'm going to then the kernel of T is equal to the solutions or let me phrase it a little a little bit fancy. The solution solution space Ax equals 0. In other words, the kernel of T will be nothing else than just solving this matrix equation. So, so if I have T of x equals Ax, this implies that kernel of T is the same as the solution space of this equation, matrix equation. That's what you need to know. So if I have a linear transformation from Rn to Rm, right, which can be represented by a matrix, then there you go. That's it. This is what you need to know. Right? All right. So that would be pretty much about the linear transformation, about the kernel of a linear transformation. Now I want to talk about something else, the range of a linear transformation. So the range, it's very important also to know the range of a linear transformation. So the range of a linear transformation will be given by the following, and I'm just going to write it directly, will be given by this. The range of, will denoted by this, range of T will be the set of all T of V, such that V is a vector in my vector space V. That is the range of T. That's basically the definition. And well, as we have seen about previous subspace, then guess what will happen? Also we'll have the following theorem, which says that the range of a linear transformation is a subspace of a vector space. Let's write it. So theorem. Let's phrase it like this: the range of a linear transformation T from a vector space V to another space W is a subspace of W. Keep that in mind. You know what the subspace is by now. Okay. And now we'll have the following corollary to this theorem, which says that if I consider now a linear transformation from Rn to Rm, right, which will be given again by that matrix representation. So let's write it. Let T from Rn to Rm be a linear transformation Okay, well, and T of X is given by AX. And then the column space of A is equal to the range of T. This is very important for you to know. And now let's see this. Let's see how this will work through some examples. Let's say example number, I think 6 by now. And let's go back to our previous example. For the previous example, okay, find a basis, and we found a basis for the kernel of T, and now we want to do the same thing, but this time for the range of T. So find a basis for the range of T. Keep in mind that so the previous example had, let me look. Let's look at the matrix. Keep in mind here now that the matrix, well, let's go back to initial matrix, look at it. I don't need to put those zeros there anymore because I'm not talking about the kernel of T, right? I'm not talking about to find out all those vectors X such that T of X will be the 0 vector. We're not talking about the kernel at this point. So if you want to look at this matrix with the zeros here, forget about it, right? So you can forget about it. That's not gonna happen, right? So we have to look at our initial matrix, which is given by this guy here, this matrix A. And what we want to do to this matrix, we want to find its row, we want to find its row reduced echelon form, right? That's what we want to do. So let's do it. Let's write the matrix again. Oh my. So the matrix A was given by the following. What was it? Let me see. 1, 2, 0. Okay, 1, 2, 0. All right, 1, 2, 0. So it will be 1, 2, 0, 1, negative 1, right? I remember the first one. Then the second one was 2, 1, 3, 1, 0. All right, the third one was, forget, negative 1, 0, negative 2, 0, 1. Okay. Negative 1, 0. Negative 2, 0, 1. And the last one was easy, was 0, 0, 0, 2, and 8. Okay, so that was the matrix. And if you want to do, well, it's quite easy to see, right? If you want to do row, elementary row operations, this matrix, and I'll leave it to you, just like the usual stuff. I'll leave it to you as an exercise. By the way, when I say I'm leaving this to you as an exercise, I hope you do it, because it's a very good practice for you for the exam. Okay. So after we do this, this will be equivalent with the following row-reduced matrix. Let's see. Oh my. So this will be 1, 2, 0, 0, -1. So the last one should be, I have to get 0, 0. So I have 1 here. I need a 0 here. So this is 1. Okay. 1, and then -1, 0, -2. All right. Then I'll have 0, 0. Let's see here. We'll have 0, 1, and 4. And the last one should be, we'll have only zeros. Okay. So I'll have only zeros here. And guess what? As you can see, the leading ones, look at them here, right? The leading ones, where do leading ones appear? On what columns? They will appear on, so let's write it. The leading ones appear on what columns? Can you tell me? So this is C1. Ouch, no. Let's write it like this. Ouch, what am I doing? Yeah, what are the columns? On which columns? This is C1, C2, C3, C4, C5. On what columns do leading ones appear? On columns, yes, like Andy says, 1, 2, and 4 on C1, C2, and C4 on the first, on the second, and on the fourth column of the row reduced matrix, right? So by the theorem here, if you look at it, we said that the column space of A is equal to the range of T, right? We want to use this, right? So the corresponding, this implies that the corresponding column vectors of A, and in this case are C1, C2, C4. Let's write them here, C1, C2, C4. So the corresponding column vectors of A form a basis for the column space of A. Form a basis for the column space of A. Therefore, this implies that a basis for the range of T is, guess what? So let's write it here. B will be what? Will be given by these columns, right? So it will be 1, 2, -1, 0. Right? 2, 1, 0, 0. And will be 1, 1, 0, 2. Right? 1, 2. Keep in mind, I only look at. Okay. All right. Now let's talk about the rank and the nullity of a linear transformation. So the rank and the nullity of a linear transformation. Okay, you see, probably you're wondering what is the rank of a linear transformation? Does it have to do? Is there any connection between the rank of a linear transformation and the rank of the matrix? Well, let's see. So let me give you the definition first. The definition is the following. Let T, and I will include both of them, be a linear transformation defined from the vector space V to my vector space W. So be a linear transformation right? Then, or let's say the dimension of the kernel of T so it's ker T, okay, is called, then let me change the call, it's called the nullity of T. That will be called the nullity of T. And it will denote this by null of T. The dimension of the range is, guess what, is called the rank of T. We'll denote this by rank T. Moreover, we'll have this spectacular theorem, which we will call the rank-nullity theorem. And this says the following, so theorem, rank-nullity theorem. And says the following, let V, let me consider a linear transformation T from V to W. So this be a linear transformation. From the, let's say, from the n-dimensional vector space, from the n-dimensional vector space V. So we know that my vector space V is of the dimension n into a vector space W. Okay, then the sum of the dimensions of the range n kernel, of the range n kernel okay, so the sum of the dimension of the range n kernel is equal to the dimension of the domain. dimension of the domain. Okay, everything that I said here, right, if you look at it, can be summarized as follows. Let me write it. That is rank of T plus null of T is the dimension of the vector space V, which we said that it's n-dimensional vector space. Or equivalently, if you want to write it in the following, the dimension of the range of T, right? Since we said by the definition here, if you look what we said, that the rank is the dimension of the range and the nullity is the dimension of the kernel. So this means this will translate into the dimension of the range plus of T plus the dimension of the kernel of T will be nothing else than just the dimension of the domain. Let me write like here, domain. That's the formula you need to know. We'll see some examples. Right? And now let's see an example. I'm going to give you a matrix and we want to find the rank and the nullity of the linear transformation, which is defined by a matrix. So let's see an example. Let me see, what time is it? Oh, okay, we still have some time left for a couple of examples. And probably I will do another video with one-to-one and onto transformations. Yeah, probably will do so. So example number, I don't even know, I forgot. What number was it? 7. I'm bad with keeping the numbers of the examples. So example number 7 says the following: find the rank and nullity of the linear transformation which is given by from T from R3 to R2, which is given by the matrix, let's see if I have enough room here. Okay, maybe I'll write it here. The matrix is given by 1, 0, -2, 0, 1, 1, and 0, 0, 0. Sorry, it's from R, what am I saying here? It's from R3 to R3. Since the matrix is given by this, right? Now pay attention. I said that the linear transformation, as you can see, so I need to find the rank and the nullity of the linear transformation, which is given by R3 to R3. And it's given by this matrix, right? So what we need to do is the following. We need to write the matrix. So the main idea is to write the matrix A in row reduced echelon form. And you will see once you do this, in fact, tricky question, what do you think of this matrix? If you look at it. Because I say here we want to do elementary transformation to this matrix. But what can you tell me directly by just looking at it? Now look at my first sentence. I said, write the matrix A in row reduced echelon form. Exactly. Like Blake says, it's already reduced there. You see? I have the leading ones here. Everything underneath, under the leading ones, it's 0, and that's it. So surprise, surprise. A is already in row reduced echelon form. Pay attention. There might be matrices which are not. This was just an easy example. Well, I didn't want to deal again with doing elementary transformation. So this was an easy example. The matrix is already in row reduced echelon form. Now the question is, the question I want to address you is, how many non-zero rows has? How many non-zero rows? How many, not how any. Jeez. Does A have? Can you tell me? How many row reduced, how many non-zero rows does my matrix have? 2. Exactly, 2. So the short answer is 2. So what does this imply? This means that the rank is what? The rank is 2. So it has, so A, so rank A will be 2. Okay. Okay. This implies what? That the rank of the linear transformation associated to this matrix will be what? Will be? Well, keep in mind, the linear transformation is that thing, T of V equals AV. So the rank of the linear transformation will be the same as the rank of the matrix, will be again 2. And now, since we know that the rank is 2, can we find the nullity? Just look at let's go back to the rank nullity theorem. What does it say? That the rank of T plus the null of T is nothing else than the dimension of the vector space. So in my case, so in our case, we'll have what? The null of T is nothing else than just the dimension of the domain minus what? Rank of T. What is the dimension of the domain in our case? What is the dimension of our domain? Our linear transformation goes from what to what? From R3, right? The dimension will be 3 minus the rank is 2, so the nullity will be 1, and that's it. So it was very very easy. Let me do another example, and I think I'll stop here for today. So another example, example 8. Let me do it quickly. And this time, let me consider the following linear transformation from R5 to R7. So this be a linear transformation. And what we want to find is the following. Find the dimension of the kernel of T when the dimension of the range is 2. B, find the rank of T. Find rank of T when the nullity of T, null of T is 4. And C, let's say, find rank of T when kernel of T is nothing else than just the null element. Okay, so this is a very easy exercise. It's just a straightforward application of the rank-nullity theorem. So apply the rank-nullity theorem. Okay, so once we do this, let's keep in mind the dimension of our domain will be what? What is the dimension of the domain? I want to hear you. The dimension of the domain is? Come on. So my linear transformation goes from R5 to R7. So the dimension of my domain is what? Is R5. So the dimension of the domain is 5. So we apply the rank-nullity theorem with n equals 5, and we have that the dimension, so in the first case, the dimension of the kernel of T is the dimension of the domain, which in our case, like I said, is the dimension of R5, which is 5, minus the dimension of the range. So this will, which is what? Which is, we said that this is 2. So it will be 5 minus 2, which will be 3. Okay? And for part B is the same thing. So we have that rank of T is what? Is n minus nullity of T, which will be what? 5 minus 4, which will be 1. That's it. And C is the same thing. In this case, the nullity of T is 0, right? So again, by the same theorem, we have that rank of T is the n minus nullity of T, which will be 5 minus 0, which is 5, and that's it. Anyway, this was just an easy application of the rank-nullity theorem. So I think I'm I'm going to stop here. Thank you very much. Let me stop the recording.